My name is Marine Faux. I am a postdoc mobility fellow from the Swiss National Science Foundation here at the Smithsonian Institution in Washington, D.C. So to briefly explain our research, we studied 6 Jurassic fossil of starfish. So the Jurassic, it's from 200 million years ago to 145 million years ago. And these fossils belong to a group that is called the Forcipulataceae. So the Forcipulataceae, it's quite a big group. I would say it's quite a big group, with approximately 400 extant species known today. And we also have like a fossil record that dates back to the Jurassic. So it has been there for at least 200 million years. This group has existed for at least 200 million years. Within the Forcipulataceae, we have a family, the Asteridae, that is like the largest family within the Forcipulataceae, but it's also the third largest family of all starfish, or also like sea stars, with approximately 200 extant species. And why am I talking about the Asteridae? It's because a lot of fossils in the fossil record in the literature were interpreted as belonging to the Asteridae, to this family. And this is the case for like the Jurassic fossils. So we thought for a long time that the Asteridae, Forcipulataceae in general, but especially the Asteridae, were originated probably at the end of the Triassic. So the Triassic, it's between 250 to 200 million years ago. So the origin of the Forcipulataceae and the origin of the Asteridae was thought to be in the Triassic or very early during the Jurassic, with like diversification, rapid diversification, very fast diversification in the Jurassic, because we don't have any Forcipulataceans fossil from the Triassic. And what happened, like when we decided to look at the Jurassic fossils, well, first of all, like when you look at them without looking in detail, yeah, they do look like extant sea stars. They do look like extant. They have resemblances with extant Forcipulataceans, extant Asteridae. But when looking in detail, they're actually pretty different. And so like the difference, we studied the skeleton of the Forcipulataceans. And if you have never seen the skeleton of a starfish, you can imagine it's very similar to the skeleton of sea urchins, because sea urchins and starfish are related. So like the dead sea urchins, like you have the test like that, this um, oval thing that some people use, for example, for home decor, the dead sea urchins. What's left is the test. And this test is made of like dozen, if not 100, of little small plates of calcite. Well, sea stars have ossicles, so they are not plates. Sometimes they're called plates, but they have ossicles, like with like a dozen different type of ossicles that makes their skeleton like that. And it's also in calcite. So, for example, if you have ever had the opportunity to touch a starfish, or if one day you touch a starfish, you will realize that even though they look very soft, they're actually quite hard. And this is because there's the skeleton under the skin. So in the fossil record, the skeleton is the only thing that's left in general. And so that's what we compared. We compared the skeleton of the Jurassic starfish to the skeleton of extant starfish. Jurassic Forcipulataceans to extant Forcipulataceans. And to do that and investigate the relationship of the different species within one another, we did a tip dating phylogenetic analysis. So it's a phylogenetic analysis that is a little fancier because we use fossils to time calibrate the tree. So we use the largest character data metrics for any starfish that have been published so far. We have 120 characters based on morphological data, and 42 species, different species, among which 13 are fossil species. So we have the 6 fossils from the Jurassic that we studied in detail, that we redescribed, and we even renamed. We named 2 new genera, Forbes asterias and Marbolaster. And we added, on top of that, 7 fossil species that are slightly younger, so fossil species from the Cretaceous and also from the Cenozoic. So slightly younger fossils for which we were confident we can score the characters in the matrix. And we have enough data to like integrate them to the analysis. And what happened is like probably like the most significance of our finding is that this time calibrated tree showed us that probably, I would say even like most likely, the Asteridae, the family Asteridae, didn't appear in the late Triassic or early Jurassic, but rather in the late Cretaceous. And this is like a 100 million year time jump. This is a 100 million year delay between what we thought happened. So we thought that the Asteridae appeared 200 million years ago, and turns out like it's probably late Cretaceous. And this is important and very interesting because it is actually very congruent. It's congruent with results that people obtain in 2011 with molecular data. So there's been a big phylogeny from marine faults in 2011, based on molecular data. So they made a phylogenetic tree of the Forcipelaceans, and they found a very interesting pattern within the family Asteridae. They found that the different clades within the Asteridae were actually like a link to their geographical repartition, which means that like 2 species were more closely related, but they were also like living more or less in the same area. So they divide the Asteridae in, I'm not sure if it was like 3 or 4 groups, with boreal Asteridae, Antarctic Asteridae, and tropical Asteridae. And I think there was also like a group of widespread one, the Sclerasterias group. And this didn't fit at all with the idea that the Asteridae, the family, appeared in the Jurassic, or we're 200 million years old. Why? Well, just simply because like early in the Jurassic, the Atlantic Ocean was just like didn't exist. So in the Jurassic, the geography we have now was, in the Jurassic, it was very different. So that was kind of weird to have a family that is 200 years old that has the phylogenetic relationship follow geographical patterns, extend like present geographical patterns when they appeared at a time where geography was just like completely different. But if they actually appeared, if the Asteridae appeared during the late Cretaceous, then the geography of the Earth was more or less the same as we have today. Granted, the Atlantic was way smaller. The Atlantic Ocean was way smaller, and a few other things that were kind of different. But this make much more sense regarding the results from the molecular data. So this is actually like this is something that I think is very exciting, that we finally managed to have a congruence between molecular data, paleontological data, and morphological data. We finally like kind of um have similar results, and we're probably like starting to have like a good understanding of what happened for this family. Another thing, another point that I think is important, if there is a 100 million year delay from the origin of the asteroid, it means that we have completely overlooked the biodiversity, the diversity of this group within this window. So we saw the fossils and we were like, oh, okay, they're just asteroids. And that's just it. Like we have the same family. We have a modern family, the Asteroidae, right now. We also have this family in the Jurassic, and so the diversity of the Forcipulataceans was more or less the same thing as we have today. Whereas what we are showing is they were different. They represent different groups. They're different form. They have different shapes. And so it's highlighting that it's a much more complex evolution and much more complex evolutionary history. We don't have the modern starfish that probably originate in the Triassic, like early in the Triassic, and then like a few million years of trying things, and then by the Jurassic, we have all the modern groups that are already here. What our study highlight is that even in the Jurassic, they were weird. They were weird and are not the same as the modern starfish we have now. So we completely, for like years, we overlooked the diversity of this Jurassic, of the Jurassic forms. And my guess would be that this, we showed that for the Forcipulataceae, but my guess is this is probably a similar story for other groups. For other group of starfish, maybe for even other groups of marine invertebrates. There's a lot more work to be done, at least for starfish that I know. But yeah, I think we still have a lot of things to learn from the Jurassic, the Mesozoic ecosystem and biodiversity, and all of this that we are learning from the past is actually helping us to understand better, to better understand what we see nowadays, like with this weird geographical repartition of the asteroid. It's actually, it makes more sense when you look at it in the past and when the family asteroid originate. So yeah, I think the past paleontology can help us, it is actually helping us understand better just like modern biodiversity and nowadays biodiversity.